So hi everybody, again, thank you all for coming, I really do appreciate it. I will be discussing, again, linear time algorithms for paired edge domination of tree graphs. Long title, but I'll get to it. So what is it? So overall, it's a study in graph theory that we're still working on. We don't know a lot about it. It's very underdeveloped, but we're making progress. So it's just another way to dominate a graph in graph theory, if you're familiar with that. So what we're doing is that we are dominating a graph by, instead of doing single marked edges, we're doing paired marked edges, which I'll show you in a moment. So to clarify, paired edge domination consists of one or more sets of paired edges. So it doesn't have to be just one pair, it doesn't have to be two pairs, it can be one or more. So for those of you who are a little bit more on the math side, we can assume the dominating set G has a perfect matching adjacent to exactly one edge. So every edge F that's not in the set, there doesn't exist an edge in the adjacent nodes. That's not dominant. So here's a picture, because pictures are nice. So on the left side we have an edge dominated tree graph, which we've already studied. We know information about that. And we can say for every edge out of the set is adjacent to an edge in the set. So that kind of explains that. What I'm looking at is paired edge domination, to where you notice instead of single marked edges we have our pairs here. And it kind of follows the same structure of single edge domination, where it consists of one or more paired edges. So a little bit of a background to help you guys out. So I use something called the Weimer edge variant. This was discovered by Dr. Jamison along with a few other people who looked at the original Weimer method, but overall what it says is that it allows us to determine the set of marked edges rather than the set of vertices. So the original method looked at vertices rather than the edges in order to see how these compositions really behaved under certain circumstances. Another important part is something called dynamic programming, where we are trying to find I'm just going to look this up because that's better, where we are trying to find the number of subtrees in a tree. So we're looking at these graphs and we're trying to break it down so we can find the minimum paired edge domination, so the least amount of paired edges that we can have in a graph. So here are my equivalence classes, and these are the classes that help to set up the algorithm that I will present. Each class has a description that overall explains what each of these classes mean. We'll be referring to these classes throughout the presentation. So let's go ahead and discuss exactly what each class is. So this is class 1, very simple. It's pretty open. Overall, it says that, I'm just going to read this off to you, the class of all rooted edge marked trees, which will be referred to as REM trees, is a minimal paired edge dominating set, and the root may or may not be incident to a marked edge. So right now we have this. In theory, we can add this to another class and it can have a marked edge. It doesn't have to have a marked edge incident to it, and that's fine. So class 2, it's a little bit more specific. It is, unlike class 1, the root is only incident to an unmarked edge. It cannot be incident to a marked edge. And this is because, the set is minimal paired edge. Donnie said the tree, so the tree minus the root. So the root is the top node right there. Class 3 is very similar. The difference is that instead of the root being incident to an unmarked edge, the root is incident to a marked edge. And that's the difference there. Class 4 is a little bit more complex, but similar to class 3, the root is incident to a marked edge, as we see RY, and the Y is incident to an unmarked edge labeled YZ. Continue on to class 5. Again, these they seem like they're building off of each other. So for this one, it's the same start. We have the root, R, which is incident to a marked edge labeled RY, which is labeled to another marked edge labeled YZ, but we cannot add, or Z will never be incident to another edge. And for clarification, when I say incident, I mean, so you have the node is incident to the edge. So, class 6, again, building off of it. Class 6 expands on 5, and it allows Z to be incident to an unmarked edge. So before, when we couldn't add anything, we now can. We can add that one unmarked edge. And class 7 is our most complex, as you can tell. It's the root is incident to a marked edge, RY, which is incident to another marked edge, YZ, which is incident to another marked edge, ZA, which is incident to an unmarked edge, and that, there we go, I got it. The set S is a minimal paired edge dominating set of the tree minus the root. So we can take that away. Okay, so this is my table of equivalence classes. What this is that it allows us to compare the classes with each other and compose them and put them together and see what happens when we do. The entries that are located on the left side of the colon represent the unmarked edges. So when we compose these graphs together, we're looking at unmarked and marked. So the ones on the left side represent unmarked, the numbers on the right represent marked. The little hyphens represent an invalid class because we cannot make it a paired edge dominated graph in any way, shape, or form. It's just not going to happen. So let's look at something called a recurrence equation. The recurrence equations is going to be what allows us to run the algorithm. So the way that this is made is that we have class 1, and to make the equation, we go back to the table and we look for a 1 wherever it is in the table. So for example, the first one is a class 1 with a class 6. And so we just have class 1 plus class 6, as we can see on the first part. So for the second one, we have a class 3 plus a class 2 plus 1. So we see it there. The difference between the two is that for the first one, the 1 was on the left side of the colon. Therefore, we can just label it as class 1 plus class 6. And that tells us this is located on the left. This is an unmarked edge composition. Whenever it's on the right, we add a 1, and that's just to tell us again, this is on the right. This is a marked edge composition, and that's how we know. So when we go through the entire table, we find where all the 1s are, and we put them together in an equation like this. So we do that for every single class. And as you can tell, some of the classes appear more often than others. So here's class 5, and it just goes till class 7. So once we have all of these recurrence equations, we can then, we'll be able to use it for our algorithm run. But first, I'm going to show you a proof to say, yes, my table is right. So here is a composition of a class 6 with a class 4. The class 6 is on the left, the class 4 is on the right. The node at the top, this one here, is going to be the new root of the entire composition. So, kind of what I was saying earlier. We're looking at two different graphs here. We're looking at a graph that's unmarked, right in between this right here. It's unmarked, there's nothing there. And we're looking at a graph that is marked. So, pretty simple. So, going back to our descriptions and what we know of paired edge domination, we know that we need to have pairs. So for the first one, for the unmarked edge, we notice that we have 3 marked edges. Obviously, there's one that is missing a pair. So we cannot add a marked edge to the right side of the composition, because if we do, that completely changes our problem. We're looking at an entirely new composition, completely. So because we can't add a marked edge, we leave it, it's invalid, rather. We can't do anything with it, it's never going to be paired edge dominated. For the marked edge though, we have 2 pairs, which is really exciting, because that's what my presentation is about. So we notice that we have the 2 pairs, but we also notice that the root is incident to 2 marked edges. And we can tell that these 2 marked edges actually have the same properties, because class 6 description tells us that the root is incident to a marked edge, ry, which is incident to another marked edge, yz, which is incident to an unmarked edge, za, for sake of argument. So we notice that we actually have this on both sides. Therefore, we're going to have a class 6 labeled on the right side, as we can see there. So we have a hyphen saying that is invalid, and a 6 saying that the overall, the composition of these 2 is a class 6. So again, you can see this right in the table, 6 and 4, we got that answer. So I'm going to present to you my algorithm run, which is hopefully simple if I explain this correctly. So what we're going to do is that we're going to label each of the nodes. Now mind you, this is just an example graph. You don't actually need the marked edges, but for the sake of the presentation, I decided to leave those in. So you can go ahead and you mark the nodes, and this just helps us as we follow along in the algorithm run. So what we're going to do is that we are going to label each of the nodes with an initial vertex. And this vertex, each element relates to each class. So we have 7 classes, there are 7 elements. And as you can see, it's 0, infinity, 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 infinity. So this is what we start out with. And what we're going to do is that we are going to work our way up the graph. So we're going to start with 9, and we're going to do 9 to 8, 8 to 7, 7 to 5, 5 to 3, 6 to 4, 4 to 2, so on and so forth, until we reach the top. So again, looking at our recurrence equations, this is what we're going to be using. And the way this works is that, again, we're starting out with our initial vectors, and here's our recurrence equation. So what we're going to do is that we're actually going to be replacing these classes based on the vertex. So as I said before, the elements in the vertex relate to the classes that were described before. So we replace the class 1 with 0, because that's the first element here. And we replace class 6 with infinity, because that's where this stands in that. So when we do it, we end up getting this equation, this new equation, which becomes infinity because we are taking the minimum of the equation. And so by taking the minimum, we're trying to figure out what the least number is. So again, 1 equals infinity. And so we're going to do this again for all of the classes. So for 2, this one we have class 1 plus class 1, so it's 0 plus 0. So the reason why the answer is 0 to this is because we're looking at each of the equations individually. So 0 is the smallest number that we have in that equation, in that set. So our answer for 2 is 0. So for 3, long, we end up getting a 1 because we have a 0 plus 0 plus 1 right at the beginning. And that's because of class 1 plus class 1 plus 1. So for 4, we're going to get infinity. For 5, we're going to get infinity. And for 6, infinity. And for 7, we also get an infinity. So looking at this all together, I took out the recurrence equations for this, we can see how all of this kind of matches up. And so we get a final vector at 8 of infinity, 0, 1, infinity, 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 infinity. Wow. So what we do with that is that we actually are going to replace our 8th node with this new vector. So before we had the initial vector for all of them, we now have a new vector that we are going to replace at 8, and so now we're going to go from 8 to 7, and we're going to use this vector instead of the initial vector. So 8 to 7, if you notice vertex 8 has the new vector, 7 is still the initial. So again, the recurrence equation does not change. We're using this throughout the entire thing. It doesn't change. But because our vertex changed, our solution is going to change. So again, now we have class 1 plus class 6, which before was 0 plus infinity, is now infinity plus infinity, so on and so forth. So when we solve this, we now get new solutions. So for class 1, we're going to get, instead of infinity, it's going to be 2. Class 2 is going to be infinity. Class 3, infinity. Class 4, infinity. Class 5, 2. Class 6, infinity. And class 7 is going to be infinity as well, giving us a final vector of 2, infinity, 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 2, infinity, infinity. So once we do this, we, again, work our way up. We're going to replace 7 with this new vector, and then we're going to go from 7 to 5, so on and so forth, until we reach the top. So when we reach the top, we get a final vector of infinity, 4, 5, infinity, 4, infinity, infinity. So what does this tell us? It tells us the final classes, which are, I believe, 4 and 5, and it tells us, hey, your algorithm runs. That's great, which is great. So that's overall what we get when we run the algorithm. So with this project, we were able to figure out the equivalence classes, the equivalence table, recurrence equations, and an actual algorithm for paired edge domination. Why is this relevant? Because graph theory is never ending. It's always growing. We're always finding new information about it that can be used and can be applied and solving new problems. So what I would like to look at in the future is definitely working with the Weimar edge variant, because really this is just skimming the surface. I believe that there's a lot more that can be done with this. In what ways? I feel like possibilities are endless, but I also would like to look at paired edge domination with other types of graphs. This specifically was with tree graphs. Tree graphs don't have cycles, and what I mean by that is that there is no place in that graph that you can loop around. It's all just branches that you just go down. So the reason why I use tree graphs as well is because it was more simple. When you look at other types of graphs, you have to worry about whether or not they're complete. whether or not they're functional, whether or not they have cycles, etc. Real world application. This question came up a lot today during my poster presentation, and at this point in time, I don't have a real world application for this. I don't. But it would be really interesting to see what this can be used for. Because again, like I said, graph theory is constantly growing and able to solve problems, and again, something that I studied and worked on, and it'd be really cool to see that actually applied. So, thank you all very much for coming.
Questions for Alexia?
I actually have a question on like Weimer-style algorithms in general.
Okay.
You mentioned on the title slide that this is a linear time algorithm. Is that time complexity comes from the fact that it's a Weimer-style algorithm and not necessarily your actual implementation of the algorithm?
I don't know the real answer for that question, but my guess is just, I don't think it's necessarily because it's Weimer. I think in this case it's because we're, like, again, this is brand new. It's a lot easier to start with linear time than it is to start with O to the n time or something along those lines. But I can't give you like an official answer because I don't actually know.
Okay. Very quickly, does dynamic programming just find one solution? Like we're talking about sort of the minimality here, right? There's a lot of different minimal sets. Does it just find one?
No, it can find multiple. Just for this sake, we are looking at